Here we are, welcome back. So the last video you watched was about high performance power plants, how to get a bigger engine into your airplane and how to be trained to act as PIC and go fly them. Well, it doesn't do a whole lot of good unless you have the propeller to realize that power and do what you want. So this episode is going to talk about controllable pitch propellers. So maybe you're, the other extreme of the single wooden fixed pitch, maybe single propeller that's counterweighted, to the variable geometry, six-bladed reversible full feathering propeller you might see in some other larger aircraft. So we're just finishing up where the last video left off, where we already talked about fuel injection systems and turbo and turbochargers. This one's going to be about the principles of propeller pitch control and everything in a constant speed propeller. Of course, your completion standards here to finish up our chapter basically demonstrate an understanding of constant speed propellers. References for this one are a little easier. Most of this stuff is straight out of your Guided Flight Discovery textbook and the AMT Power Plant Handbook, which is going to be linked in the video description below, and this awesome pamphlet from Macaulay Propellers, who put out some excellent resources about how their systems work. So you'll see a reference to their old manual and their updated manual as well. So let's start out with, why do you need to know about controllable pitch propellers? Well, because you want to fly bigger, cooler, faster stuff, for one. Two, because you're going to need to get your complex endorsements to get your commercial check ride. You don't have to do it in a commercial aircraft any longer, but you have to have your complex endorsement. And one of the ways of getting a complex endorsement is to act as PIC of an aircraft with retractable gear, flaps, and a controllable pitch propeller, such as the Lake Amphibian here. You need to have a complex endorsement. It needs to have all three of those things, or there's a whole bunch of other derivatives down there, including seaplanes that have a controllable pitch propeller, but they don't have to have retractable landing gear if they're a full-time flow plane, and a few other conditions there. But let's talk about the 61.1 definition of a controllable pitch of a complex airplane. What you have to do to become pilot in command of a complex aircraft, and that's what 6131 talks about. Basically, just like with high performance and tail wheel and high altitude, you need ground training, flight training, and a one-time endorsement, and you can fly any complex airplane out there. So let's start from the simple and move on to the complex. The simple is the fixed pitch propeller. It was always a compromise. Fixed pitch propeller was between do you want to take off and climb, or do you want to cruise? So you can kind of think of it as having a beach cruiser, a bicycle with one gear. It's going to be hard to go uphill. You're not going to be able to go that fast. And then once you do get on the open road or go downhill, you're not going to be able to pick up speed because your feet can't go that fast. So you kind of think of it as being stuck in one gear. I put a little star next to it because there's no gears involved in this one. Now here's the components of your fixed pitch prop that you probably learned how to fly on, but now you want to fly something a little cooler and better. So we end up with a controllable pitch propeller. Controllable pitch propellers are the best of both worlds. You can have a takeoff propeller with very low pitch and let you go to high RPM and climb out a steep angle, and you can have a cruise propeller which lets you go fast. So it's equivalent to having gears in a bicycle, to where you can kick into low gear and go uphill, but you can kick into high gear and go fast when you're on the highway, or a car if you're into that kind of thing. All right. So one of the ways they describe it is it's the ideal potential and use of power. So another way of thinking it is the right propeller for everything that you want it to do. You can kind of think of it as multiple gears, but once again, there's no clutch, there's no shifter, there's no gears at all in this thing. It's all about the propeller changing pitch. And we see here from the AMT handbook this picture showing us how this is a variable pitch propeller, and it goes all the way from having zero angle of attack or a pitch angle between the chord line of the propeller and the relative wind, to negative to go backwards, to a little bit forward, to a little bit more forward, like in flight idle, to maybe cruise flight where it has taken a much larger bite of air on every revolution, or in most multi-engine aircraft will have a full feathering propeller, so you can feather it where it goes almost straight 90 degrees to minimize the amount of drag in case that one engine quits. Pretty cool stuff, it really is. So we have to talk about some terms to make sure we're on the right page here. So let's start with geometric pitch. That's the distance the propeller would advance if it was in one revolution if it were in a solid. So how far the propeller should go if it was cutting through a block of wood. Effective pitch is how far it actually goes through the air. What actually happens in real life. And then slip is the difference between those two. Then one more term that's a little harder to find in some of these places, propeller efficiency. That has to do with how much power is output from the engine compared to how much thrust is produced by the propeller. So I don't think you have to memorize all that without a picture. Here's a picture. If a geometric pitch is how far it should go in one revolution, again, if it was cutting through in theory, effective pitch is how far the aircraft actually goes in one revolution, and the difference between those two is propeller slip. Here's what the cutout of a two-bladed hub looks like, and I'll do my best to describe it here without actually going out in the hangar at Miramar College and showing you all the wonderful toys that we have. So you have two propellers, obviously one on each end, and they're connected in the middle here. The row of bearings and the row of the seats here hold them in place so they don't fling off from centrifugal force. And inside, you'll kind of see this propeller is connected by a cam right here to this piston. And if you can see down here, this propeller is connected by this lug down on the bottom. So when this piston moves in and out, it's actually changing the pitch on both propellers the same amount. It's kind of like the tail rotor on a helicopter. And those are a little easier to see than cutting apart your own propeller hub. It's oftentimes charged with a spring in this case. Sometimes you'll see a nitrogen precharge out here. Sometimes there are counterweights on the propellers, and that's all to make different aerodynamic twisting actions to either make it feather or make it go to flat pitch. Depends whether it's a piston or turbine, multi or single engine aircraft stuff. But the basic concept that we're going to keep coming back to here is engine oil would go into this hub cavity and it would move the piston backwards in this direction. As the piston moves, it changes the pitch on both propellers the same amount at the same time to increase or decrease pitch. On single engine applications like this, oil increases the pitch of the propeller. And you think of it as, what do you want to happen? If you lose engine oil, you want these to go to their high RPM or their first gear, takeoff or landing position. A little different in multi-engine airplanes. So you look inside those and they're way different. Most of this discussion is going to be talking about the controllable pitch propeller on your single engine piston airplane that you probably got or will get your complex in. In a few videos from now, we're actually going to discuss full feathering propeller. We'll talk about them today, but we'll talk about multi-engine systems later on in this course. So here's how you control it, all right? So you can't get out there and cut your propeller apart in flight. You can't get off and take off in the air. You can't take off a climb prop and put on a cruise prop. So what you do is you can control it right here with your propeller control knob. Most of your private pilot training, you had a throttle and a mixture, and that was probably it. And now you have a throttle, prop control, and a mixture. You'll see right here and where they are on the Piper that we're looking in right now. Here's your RPM gauge. Before, your throttle ran the RPM. Not anymore. Now the propeller RPM or the RPM controls the RPM. When you're moving your throttle, you're actually moving your manifold pressure. And so there's your manifold pressure is your indication of your throttle. Your RPM is an indication of your RPM. And then actually down here on the Piper, your fuel flow is an indication of the mixture. What else? In the coming videos, we'll talk about landing gear and everything else you should already pretty much know in here. So basics of we already know what manifold pressure is. We discussed that in our last video. RPM, revolutions per minute, that's how fast your propeller is turning. So one of the first things you need to remember, you really need to wrap your head around this, is when the propeller controls push forward or pushed in, you're telling, in essence, you're not actually changing the pitch of the propeller, but you're telling the propeller governor what you want the propeller to do, and it does it for you. We'll get into that in a second. So everything works like it's supposed to. You push the blue knob forward, those propellers turn to a low pitch position, which lets them go to higher RPM. So high RPM, prop control forward, The propeller, as it goes to a higher RPM now, think, giving it gas when you're trying to go uphill before you're dropping the clutch and doing burnouts, whatever it is. You're trying to spin the propeller faster, and every time it spins, it's taking smaller bites of air. It's taking smaller steps when it goes uphill. As you pull that prop control back or out, you're asking that propeller to go to a higher pitch position, which means every time it revolves, it catches more air. More air slows down the propeller, and it turns it to a low RPM position. So low RPM equates to high pitch. High pitch equates to low RPM. And here's where we're talking about our pitch angle is the chord line of the propeller and where the relative wind is coming from. That is the angle of attack. When we talk about the pitch angle, it's the angle between the chord line and the plane of rotation. It would be equal. If we're talking about the wing, it would be the angle of incidence on a wing. So again, here's kind of how you'd run the blue lever. Thank you, the folks at Bold Method, for helping us out with these excellent articles and with these excellent graphics. And you should, by all means, go to Bold Method and subscribe to their channel. I know I do. I get excellent quizzes a couple times a week. I've learned a lot from them, even as a flight instructor. And if nothing else, you might pick up something along the way. And it's free 99 to you. Okay, you push the prop control forward. We'll talk about the speeder spring, and we'll talk about the governor in a little bit. But basically what you're asking it to do, you're asking it to go to a lower pitch position. And let's contrast here, since we see them side by side. When you pull that prop control back, eventually what happens is the propeller pitch angle increases. So this would be more of a cruise configuration because you're in high gear, if you want to think of it that way. Every time this propeller rotates, it catches more air. Or since more air is going fast, you're keeping the same angle of attack, but it takes a higher pitch angle to do that. We'll come back to the governor and the pilot valve and how oil moves to and from it in just a minute. So a nice animation. Once again, thank you, Bold Method, for how it happens. If you think back to the other picture, we saw the piston. We saw how the piston was connected to a blade. And so when oil gets pumped from the engine, from the prop governor, and most of them have a boost pump. As oil gets pumped out into the propeller hub, you usually see the spinners bigger on these type of aircraft because it has a lot of moving components in there. It moves the piston, and as it moves the piston, it changes the pitch on the propeller blade. It's pretty awesome, amazing system. It gives you so much more speed and cool points. So here's what I kind of try to draw out for you. So here's the PA-28, the Piper Arrow. The Arrow 3, actually, I think is what this one's from. So 30 inches from the hub. So there's actually a part on the propeller blade. In this example, it's 30 inches from the hub is where you check the pitch angle. And the lowest amount of pitch compared to the ring gear here, the flat spot of the crankshaft, the lowest pitch when you're as low as it goes is 15.3 degrees. And that's where we make sure every annual inspection we double check this and make sure everything's working like it's supposed to. So this is as low as it goes. It's pulled over. It can't pull over any farther. When you push the blue knob forward, it will never go less than 15.3 degrees. It always has some kind of pitch in there. You need some thrust to take off and to land. But then as you get up into airspeed and you start pulling that blue lever back, if you were to pull that blue lever all the way back, and the most pitch angle you would get out of your PA-28 is going to be like 35.4 degrees. The PA-28 is not an extremely fast aircraft. If it were, it would need a higher range here of pitch to move. But because it's kind of clunky and heavy, and I love arrows, don't get me wrong, but there are faster planes out there to have, and those faster planes have more angle available on their propellers to them. And this is just for reference. The zero, that's just, this propeller never goes to zero. I know you saw that a few slides ago, and that's actually going to be in your usually turbine aircraft, an aircraft that you want zero thrust on, or aircraft that you want to be able to go reverse thrust on. So there's our RPM gauge. Once again, your blue knob is basically going to be in charge of here. There's some caveats to that. When we're at low power settings, like when we're taxiing around, the throttle acts just like it did in your fixed pitch prop. Because again, this can only go down to 15 degrees. It can't go down any farther. So when you're just idling at taxi speeds, it's not increasing pitch to do anything. Once you go fast enough to where when the governor and everything's working and it tries to maintain its own speed, that's when it would increase pitch to keep from overspeeding. And it's not going to happen until the run-up or somewhere in the takeoff run. A few things about the tachometer, your RPM gauge here. This is usually where your tach hours are, and this is what your maintenance is based off of, or the tach hours. Usually there's another Hobbs meter over somewhere else, and that's the one you're paying off of that's powered off oil pressure. But maintenance in your car is done off your odometer. Maintenance in the aircraft is done off the tachometer. Manifold pressure gauge, we learned about that in the previous video. This is measuring the suction, or the air pressure inside the intake manifold before it enters the engine, after the turbo, if there's a turbo. Looks like this is for a normally aspirated aircraft because, or at least a turbo normalized aircraft, because the red line is right around ambient air pressure anyway, 29.92 or around there. We're looking at 23 inches of manifold pressure. We'll just call it 23 inches pretty much from now on. And on the RPMs, they're in hundreds of RPMs, so this one's at 2400 or 24 when we're speaking short tongue in the aircraft. So once again, the throttle is going to be in charge of your manifold pressure, and your prop control is going to be in charge of your RPM. Now, what I'm talking about up in the governing range, when you're taking off and flying, and this is going to happen. When you're just idling around on the ground, it's a little different because, again, you're not making enough RPM for the controllable pitch propeller, constant speed propeller, the governor, and everything else we're about to talk about to do any good yet. You already saw it on the PA-28, but here it is again, your manifold pressure gauge, your RPM gauge, two different gauges, two different knobs run them, and then Piper was pretty sneaky and added a fuel flow gauge in gallons per hour down here too. And basically, you can use the mixture to kind of get you close when you're in cruise power settings during your 75, 65, or 55% power settings. Get you close, but there's better ways to fine-tune that mixture. Okay, so we keep going back and forth. So let's talk about really quick a controllable pitch propeller versus a constant speed propeller. A controllable pitch propeller means you can change the pitch of the propeller in flight. There are such things as ground adjustable propellers, but those aren't controllable pitch because you cannot do it in flight. So controllable pitch, or think old propellers. You had a lever that physically changed the angle of the blades. By newer technology, I mean since a long time now, we've had constant speed propellers, where there's a governor, a very awesome component that automatically changes the pitch of the propeller blades to maintain a constant RPM. So a constant speed propeller is probably what you're going to learn how to fly, and you probably will very rarely fly a controllable pitch propeller, at least until you get some buddies with some vintage aircraft. So how's that happen? Well, here's the governor. The governor is the kind of magic behind this. Here's a picture of the governor on the aircraft. The Cessnas love to put it in the front so you can see it and pre-flight it. It gets cool air onto it. Pipers love to hide it in the back behind the engine so you'll never see it. But that's what it looks like. The blue lever would connect right here. You see how when you manipulate the lever forward and back, it's actually increasing or decreasing tension on this spring. It's that simple. You're moving the blue lever. All you're doing is changing the tension on the speeder spring. That's it. Let's look over here at a little cartoon cutout animation of it. You're moving the lever. Here's the speeder spring. So when you push or pull it one direction or the other, you're making more tension or less tension. What's happening is what we're trying to see here is as these counterweights, these flyweights are spinning, because this is geared to the engine and it turns with the engine, they end up with some centrifugal forces trying to make them go out. If there's more tension on the spring, these counterweights go in, and that tricks the engine into thinking it's not going fast enough. It decreases pitch on the propeller, still it speeds up, and they go back to this on-speed condition. If you then want to decrease the pitch on the propeller, you want the propeller to go to a lower speed, then you trick it into thinking it's overspeeding. and you would move the prop control in the other direction. It would decrease the tension on the spring. These counterweights would then fly out, tricks the engine into thinking it's going too fast. It changes the pitch on the propeller to then slow the engine down. Whew, that's a long knee bone's connected to the hip bone here, so let's use some other graphics to figure that out. So again, this propeller is always looking for an on-speed condition. The governor wants to be just right, not too hot, not too cold. And it does that again when it's turning, when this thing's up in operational speeds. These two flyweights want to be vertical. That's on speed. And that's what this wants. When it's on speed, the pilot valve is blocked. There's no oil going to or from the propeller. Everything stays right where it is. This oil stays there. Oil in the engine stays in the engine. Nothing moves around. By the way, yes, it's engine oil that moves these, so it works a little faster once the engine's warm. The propeller is a little sluggish when the engine's cold. And here's kind of indicating our boost pump that works through the governor as well. What we saw here before, we saw the spring that puts tension on the piston. Oil moves the piston back. The piston's connected to each propeller, which causes them both to turn simultaneously, or all three, or all five, or all six. So you're tricking it into being underspeed, or you're tricking it into being overspeed. So when you increase the tension on this spring, the counterweights move inward. And that's tricking the governor into thinking it's not going fast enough. It wants to speed up to get these counterweights to go back out where they were. If you were to be able to see, the bottom of these flyweights are connected to a pilot valve, which is going to move up and down. As this device moves up and down, it either lets oil come from the propeller back to the sump, or on the other side here, you saw the pilot valve move up. It lets oil go from the engine out to the propeller. Okay, so let's compare these two. Under speed, the flyweights go in. It thinks it's not going fast enough, so oil comes from the propeller. That decreases the pitch on the blades. That lets the engine speed up. And this either happens because you're tricking it into thinking it's not going fast enough, or let's say you're flying along and you pitched up and your airspeed decreased, your RPM decreased. This actually happened. Kind of like a CVT in a car. When you go up a hill. All right, let's go over here. Let's say overspeed. This happens one of two ways. Let's say you're flying along straight and level. You then, without touching anything, lower the nose and the aircraft speeds up as it descends. That's going to cause the engine to increase speed as well. That would cause it to overspeed. I don't mean like red line blow up overspeed. I mean it's going faster than what you told it you want it to do. When that happens, it speeds up, centrifugal force moves the flyweights out, the flyweights move the pilot valve up, oil goes to the engine, to the propeller, from the engine to the propeller hub, the piston moves, it increases pitch on both propeller blades. As they increase, they cause more aerodynamic drag, and that slows the engine down until they're back on speed again. Okay, so underspeed happens because let's start with overspeed. Overspeed happens one of two ways. You added power, and momentarily the engine, sure enough, did speed up, and then it increases pitch on propeller blades to slow it back down to where you wanted it to be. Or you pitched forward and you descended and picked up airspeed. It's going to increase pitch to keep the engine from speeding up. That's why we call it a constant speed propeller. And this thing does it all for you. Here's an excellent graph. Thank you, folks at Bold Method, once again, of when you overspeed. Once again, when you add the throttle, or if you start to descend and pick up airspeed, the engine's going to increase in RPM. I mean, 1 RPM is an increase. When that happens, the flyweights go out. They're connected right here to the pilot valve, and you see as the flyweights, as the little legs on the flyweight go up, it pulls the pilot valve with it. Oil then goes to the propeller, increases the pitch, which then slows the engine down. It gets back on speed again. Let's go to the other extreme, the underspeed condition. This happens for one of two reasons. Let's say you're flying along and you pitch up without adding power. The aircraft slows down, the engine slows down. Now it senses that it's not going fast enough anymore. And when this happens, it's actually going to, in this example, move the pilot valve down. It lets oil, the The spring here pushes the piston. It squeezes oil back out of your return lines through the pilot valve back into the engine where it can filter with the rest of the engine oil. It allows the pitch to decrease on the propellers. The propellers then speed up back to the on-speed condition where the flyweights are back to neutral, and it shuts off the flow of oil to and from the propeller. Here's our thank you again bold method article on, did it have 2 over speed? This sure did. This isn't on them, this is on me. That's supposed to have an underspeed where it goes the other way. But you can, instead of me describing it again, you can go back and rewind it and watch it again if you want to. Okay, so magic stuff. All right, it's not magic. It's pretty simple. It's physics. It's centrifugal force. When things speed up, flyweights tend to sling out. You just connect it to a pilot valve, and it changes the pitch on the propeller for you. So kind of, I'll sum it up in the end. So let's talk about a few more terms. Okay, so full feather. Here's a picture of a full feathering propeller. These things went to 90 degrees each. Most multi-engine aircraft will have it this way, and you see a lot of single-engine turbine aircraft have a feathering propeller. It's works to minimize drag, but that's not really what it's there for. But a multi-engine aircraft, it is so you don't have a big 10-foot air brake out here when you have one engine quit. So if this engine fails, turns off, or is shut down, the propellers will feather like they are right now. Okay. Now here's you see twin engine, 2 throttles, 2 mixtures, 2 props. Starting 80s on, I think 70s on, you would see 2 smooth black throttles, you'd see 2 blue knurled knob prop controls, and 2 different textured red knobs for mixtures. So obviously people would have a hard time. They would confuse the props and the throttles quite a bit. But here's your propeller control on, actually this is on a Mixmaster Cessna 337 because it has a front engine and a rear engine. It's still multi-engine, but you want to be able to feather. And all you have to do is that prop full forward is high RPM, prop back is low RPM, prop all the way back is feather. That's all you have to do to feather this engine, is pull that prop control all the way back. Okay. You also hear beta, and this is generally going to be turbine. That's pretty much the only Macaulays that go to beta are going to be on turbine aircraft. So in beta, they're being used to taxi. It's instead of increasing RPM to increase thrust, the RPM stays constant, and they just vary the propeller angle for a little bit of taxi speed or a little bit of reversing speed. As opposed to the planes that you're probably flying right now, you increase the propeller, you go forward. Well, when these turbine aircraft are spin up to their ground idle speed, or their flight idle speed, but in their ground idle speed, they just makes very small changes in pitch, and that's going to get their taxi speed. You'll definitely hear this. Next time you go to the air show, listen to a C-130 taxi around. You hear this. It's very obvious when they come in and out of beta. Don't confuse beta with reversing. Okay, so that's when it will go to negative pitch, and you can actually back up a C-130 and other propeller aircraft with beta. This works great for slowing you down after you land. It also works great for backing into parking spots, but it's most often used after landing for reverse thrust to help slow the aircraft down. Okay, so here's just some examples you might see. Here we got flight idle and ground idle. So in this turbine aircraft, this graphical image of it. It's not a mixture control, it's a condition lever. Okay, do you want that thing to be off and feathered, or do you want it to be on or max? It's what condition do you want that turbine engine to be in? It's not a mixture because it does its own mixture control. But then over here we see our power control, or our thrust control lever. You would have your ground idle position, click it into flight idle about to take off, and then from this point it's just like a regular throttle. However, you click it back into ground idle, and then you throw it into reverse, and now it's actually providing thrust, pushing air forward away from the aircraft. And it doesn't turn the engine backwards, right? It pitches the propeller pitch past 0. while the engine rotates in the same direction. Okay, so enough about all the technical aspects of it. How do you in the cockpit do make it do what you want to do? Well, that's with the blue lever, obviously. Um, and again, so hopefully now you kind of understand a little bit more. When you, as the pilot, want to increase or decrease RPM, you move the blue lever. You're tricking the governor into doing what you want it to do. So it's a good general rules of thumb here when you want to increase power. So let's say when you want to you want to take off, you want to make sure these are all in this position. And then let's say also same time, what if you're cruising along at cruising altitude and you want to then increase power to climb to a higher altitude? You should do it in this order and only this order, as long as all these components are there. When you want to increase power, so let's say before you take off, one of the last few checks I do, I make sure the cowl flaps are open. I make sure the mixture, prop, and throttle are forward. So basically, I start with my right hand down if I'm in the left seat. And so whichever seat I'm in, I start with down at the bottom by the cowl flaps, make sure they're open, and then I go right to left on the instrument panel. Red knob forward, blue knob forward, and then black knob forward. So you increase power right to left, if you want to think of it that way. Now that we've taken off, we've climbed, we've got to a new altitude, you did your pitch pause, you did your pitch power trim mixture is what you'll probably learn in your fixed propeller simple aircraft. You pitch the nose forward, you set your RPM where you want it, you adjust your trim so you don't have to keep pushing, and then you adjust your mixture. Well, now in faster aircraft specifically, it's going to be pitch, pause, power prop, trim, mixture, cowl flaps. So yes, I just doubled the steps that it takes to level off from a climb for quite a few reasons. So let's talk about this. So you pitch forward to stop climbing. That part hasn't changed. Now you need to pause. You need to let that thing build speed. Okay, so as opposed to your 172 climbs at 85, cruises at 105. Not a big difference between the two. You start flying at 210, you're going to climb at 110, you're going to cruise at 160. So you have a lot larger airspeed changes between climb and cruise. So the pitch forward to stop the climb, pause to let the airspeed build. Power, you move your throttle back. Prop, back to the RPM you want. Trim, because right now you're pushing forward dramatically on your faster aircraft because you've just increased 40 or 50 knots of airspeed. And then you do your mixture. You probably do trim again, to be honest with you. And then you close your cowl flaps. Because now that your engine has had a chance to cool off at cruise power while you sped up, you want to close the cowl flaps, start getting a little bit more airspeed from it. And now that you're cruising and you want to begin descending, okay, so generally what you do is you pull the throttle back to begin that descent. You don't necessarily have to pull the propeller back. You can leave it where it is because remember the governor is going to do his job and keep the RPM where it is. Be a friendly flyer and lower your RPM when you're flying around people in populated areas because a lot of that engine noise comes off of that propeller. So by lowering the RPM is going to make you much more amenable to your neighbors. And then so this doesn't really work for descending, I guess is what we're getting at. But when you are going from climb power to, or from takeoff power to climb power, or more specifically from climbing power to cruising power, you're going to reduce everything left to right. Throttle back, prop back, mixture back, cowl flaps closed. You go out and do your first controllable pitch flight with your CFI. I know what I make my students do. You climb to 1,500 feet, you level off. You're going to do pitch, pause, power prop, trim, mixture, cowl flaps. Okay, great. Let's start climbing. You start at the bottom. Cowl flaps in, mixture in, prop in, throttle in, and then you pitch up and you start climbing. You climb another 500 to 1,000 feet to another altitude. Pitch, pause, power, trim, mixture, cowl flaps, and then you do it all over again. The more you practice on the ground, specifically in the cockpit, a lot more money you're going to save yourself in the aircraft. Or you could just get a FADEC and it does everything for you. So FADEC stands for Full Authority Digital Engine Control. It controls the pitch of the propeller for you, so you don't have to. You don't have to adjust mixture because it does it for you. And it's pretty awesome. They're expensive. They're you're letting Skynet fly your plane for you. Not really. I mean, it's mostly mechanical with very digital input. But they're out there, so now you know what FADEC stands for. So what do you look for on propellers? Now that we've talked about the inner workings of the governor and what you do when you're pushing the blue lever around and the order that you do them in. So let's just talk about start to finish in a flight. All propellers, what you're looking for are nicks and security. Just like on your fixed pitch propeller, the new thing here is oil leaks. Remember, it's oil that goes in and out of the propeller hub that changes the pitch of the propeller blades. So if you see oil slinging out of your propeller, there's probably a leak in that seal somewhere. If you see oil flowing all over your windscreen or down your propeller blades, it's usually coming from the O-rings that where the propeller meets the hub, or the O-ring between where the oil is inside the housing where the piston is. You don't want oil leaks, is where we're getting at. A little bit's okay, just a lot's not okay. When you start them, it's you just push the blue lever forward. All right, so pretty much the entire time on your ground, that propeller control is going to be in high RPM/low pitch position. Make sure you remember that high RPM doesn't mean high pitch. High RPM is low pitch, low RPM is high pitch. So I'm going to pretty much go back and forth between a bunch of different types here. This is a BE76, a Beach Duchess, and this is probably going to be in about a 172 RG. So again, high RPM is full forward. While we're here, you'll notice the Beach 76 says not to pump the throttles during starting, and then you see the 172 says go ahead and pump it once, hey, up to 6 times if you feel like it, and go ahead and keep pumping that throttle if you want to. So just like we talked about before with mixture, let's talk about, do you pump the throttle when you start or don't you? I could jump on a soapbox and we could be here all day, but you can do some research on your own. In the end, and so feel free to check out each one of these websites or just do Google searches for your own. In the end, the best thing you could do to find out is do whatever your POH says. And here's a great example. The Beach 76, if you pump while starting, you could cause a fire. So don't do it in a Beach Duchess. On a 172 RG, it doesn't, go ahead and pump before you start. And then while you're cranking, it doesn't really say anything about that. Now, and it really comes down to this. It's if you read this, you're going to say you should never pump throttles while you start. But if you read this, you should say you should pump the throttle a whole bunch of times before you start. And it depends. The 172 RG doesn't have an accelerator pump. The 182 RG has a side-mounted carburetor. And it depends on the installation. It depends on that carburetor. It depends where it hooks up to the engine. And it depends what that engine manufacturer and that aircraft manufacturer have said. I will say in many, many, many carbureted aircraft that I have started, I will get in it, and before I even start cranking it, I will go ahead and move the throttle at least once, and I look for resistance. If it sat there for a long time, when you pump the throttle, the first, the one time that I always do just to see, you'll actually feel when the air shoots out of the accelerator pump and when fuel gets to it. That's good. I don't need to keep pumping it. I know that now there's fuel in the carburetor. If you move the throttle and it feels like it's not moving any fuel, it's probably not. Either there's no accelerator pump in that carburetor and pumping it's not going to do any good at all, or there is an accelerator pump and it's broken or it's full of air. So the best thing you can do is talk to a mechanic about your installation in the airplane that you're flying and figure out what's the best thing to do for it. All right, so feel free to do some more research on that. Okay, what do we do with propellers? So kind of, again, we start, and as we're going from our starting spot to our taxi to our run-up area, it seemed like nothing's new. If you increase throttle, it increases RPM. If you decrease throttle, it decreases RPM. That's just because it's idling. It's not in what's called the governing range yet. Now you get to the run-up area, and you run up to about 1,700 RPM here in this aircraft, and then you check the propeller. What you do is you cycle it. You grab the blue lever, and you pull it all the way back, and then it's going to then do everything we just talked about. It's going to trick it into thinking it is overspeeding, so it's going to then move the pilot valve, move oil to the propeller hub. It's going to increase the pitch on the propeller blades, and then it slows them down. And then you'll quickly push it back forward again, so you don't bog the engine down for no really reason. You're just making sure that everything works. You're looking for three different things. You're looking for an increase in manifold pressure, you're looking for a decrease in RPM, and you're looking to make sure that oil doesn't spray all over the window when it comes out of the propeller. You'll probably get taught to do this 3 times, but it's not necessary. When you're first learning how, or if it's the first flight of the day, it's nice to get warm oil out there, though. But if it's a flight training aircraft and it's the 5th flight of the day and every student cycles it 3 times, you're just going to wear out components for no real reason. But again, on that one, I don't care. Do whatever your flight instructor tells you to do. During takeoff, it's going to stay full forward. Okay, so everything right to left when you add power, right? Mixture is in, prop is in, throttle goes in, and you take off, and you're just making sure that it's 2,400 RPM. And as long as the governor is doing its job, it will be. If you abruptly move the throttle, however, the reason I keep going through all these steps. You push the throttle forward, the engine overspeeds, the governor senses it, it moves the pilot valve, oil goes to the hub, it increases pitch on the propeller, which slows the propellers down again. The reason I go through that so many times is so you can hear it enough times, and so you realize that there's a few steps between you moving the throttle and the props moving to respond to you. So nice, gentle throttle movements will keep the RPMs from increasing or decreasing too drastically. You'll see a few questions, and I kind of gave you the best answer for all of them. When you're taking off and when you're climbing, when you want the most power out of that engine, I mean power, thrust, not speed, you need to be full forward, which puts you to a low pitch, high RPM position. Like for takeoff, you need full forward, which is low pitch, high RPM. All right, so we've climbed, we've got to our cruise, we pitched forward, we paused, we gained some speed, we pulled the throttle back somewhere between 15 and 23 inches on manifold pressure in this installation, and then the RPM. You get to pick somewhere between 21 and 2400. As long as you're not using more than 75% power, the Beach Duchess here doesn't care. Anywhere between 15 and 23 inches with a throttle, anywhere between 21 and 2400 with the RPM, feel free, have at it. It's up to you. Whatever sounds good, whatever feels good. And I'll be honest with you, most airplanes have kind of a sweet spot for RPM. It's usually around 2,300 RPM. I like how it sounds. Most engines run pretty well that way. But some don't. Some run better at 24, 182s, for instance. When you bring it all the way down to 2,100 RPM, you bring in a pretty good neighbor. You're burning less fuel, which also might not be going quite as fast either. And then, of course, we talked about that in the last video, make sure you lean the mixture at any altitude if you're cruising. So let's see down here. Let's see some examples. Okay, so if we're at maximum power, you want the highest RPM. It's going to give you the most fuel burn, fuel consumption, but you can be at the highest RPM, making the most amount of noise, but also the most power. They recommend you pull it back to 2,500 RPM for cruise power, and they recommend you pull it back to 2,300 RPM. That's their recommended cruise power. You see, they're the exact same. Recommended cruise power, recommended cruise power. In other words, it's up to you. Whatever sounds good to you. 2 different aircraft, by the way. This is, I think this is a 182 RG, and this is the Beach Duchess down here. Or economy cruise, go ahead and pull the throttle back and pull the RPMs back. And then, of course, once again, lean as required. It doesn't say as desired or if you want to. It says lean. All right, so how do you know what RPMs and what manifold pressures to choose? Well, you look in the POH. So here in our 182 RG, or the retractable 182, the cruise performance charts are way more complex. Okay, there's 6 pages of cruise performance charts because for every altitude you have different RPM and manifold pressure settings. You're 172, and then all altitudes fit on 2 pages. Here it takes 6. So let's just kind of walk you through this one. You still got the same standard column, 20 degrees below standard, 20 degrees above standard. You still have the same brake horsepower, not 2 airspeed gallons per hour, but the difference here is you get to pick between 2,400 RPM, 23, 22, or 2,100 RPM. And each one of those, a set manifold pressure will give you a certain amount of power. So if I want to fly along at 4,000 feet pressure altitude, and I want to get my maximum 75%, and that's the max recommended power setting in this airplane, I'm going to set it at 2,300 RPM, 23 inches of manifold pressure if I'm on a standard day, because that gives me 75% power. There are other ways of getting it. I could be at I could go at 2,400 RPM and 22.4 inches of manifold pressure, and I'm going to be right around 75% power. But if I'm going to go a little faster, but I'm going to burn more fuel, and I'm going to make a little more noise. But you do basically notice the lower the RPM, the lower the power output, and the lower the speed, lower the fuel consumption is going to be. So it's all what you want. Do you want to go a little faster and burn a little bit more fuel? Do you want to maybe go a little bit slower? I'm talking 3 knots slower and burn a little less fuel, a little less wear and tear on the engine. So yeah, now like this, for instance, we call it 2323, or we call it 23 squared. In other words, 2,300 RPM, 23 inches. That's what we mean by 23 squared. Another thing your flight instructor might get mad at me about by calling them out on is you probably had a flight instructor telling you cannot operate over squared. What they mean by that is you can't have the manifold pressure higher than the RPM. And that is completely not true. You can watch some Pelicans Perch those Pelicans Perch articles from AvWeb do a great job talking about that. Basically, it's a throwback from old radial engine days, where it actually would wear down one of the bosses, the main boss inside that engine. For your flat engines, like your horizontally opposed engines, like the one in the 0540 here and the retractable gear 182, look, it's on the chart. You can run 23 inches at 2,100 RPM. You could run 23 inches at 2,200 RPM. If you couldn't do it, they would not put it in the chart. So when your instructor says never operate over square, send them to AvWeb and have them read some Pelicans Perch articles, or simply just break out the performance chart sheet here and ask them why it's there if you cannot do it. Again, not to prove anybody wrong, but okay, why? Yeah, that's wrong. So it's okay to operate over square. It's just not okay to slam the throttle forward when you're stuck in a high gear, just like you wouldn't do it in your car. You can't pass a car on the highway if you're still in overdrive when you go to pass it. You need a downshift a gear to do it. Same thing in an airplane. When you add throttle, you need to increase the RPM first before you increase the throttle. Okay, so we'll talk more about performance charts here in a few videos as well. Now let's jump up here to 8,000 feet and just see what we're looking at. So obviously the standard temperature here at 4,000 was 7. The standard temperature at 8,000 is -1. That's the standard. That's what it should be. That's the ISA is 15 minus 16 because it's 2 degrees per 1,000 feet, which brings you down to -1. If you don't remember that, go look through your private pilot performance charts and your weather stuff. So how come at 8,000 feet, even at 2,400 RPM, the highest the chart goes is 21 inches of manifold pressure? In other words, the air is so less dense at 8,000 feet that even full throttle will give you at most 21 inches of manifold pressure. Think of it this way, the atmospheric pressure at 8,000 feet is only 21.00 inches of mercury, or somewhere around there, because the air is less dense. Because there's less air, you make less power. Look, we're going about the same speed. Holy cow. So here we are. It's only 7. Well, let's look at our 23 that we did before. We're going 150 knots, burning 13.5 gallons per hour. Even at full throttle at that altitude, we're only getting 21 inches of manifold pressure, and at 2,300 RPM, we're going faster while burning less fuel. So again, you want to get up as high as you can go, because with less dense air and less air resistance, you're going to be able to go faster and burn less fuel. All right, so I just can't get off of this one. I can't let go of this bone. Make sure you lean if you're cruising at any altitude, and make sure you lean if you're cruising at any altitude. Now, before landing, you want to make sure the propellers are in high RPM. So you're going to see propeller, high RPM, propeller, high RPM. Now, this doesn't mean like, all right, folks, we're going to start to descend and land now, and you shouldn't shove the blue lever forward. This means sometime before you land. Generally, I will do this on base or final is when I will move my propeller control forward. And we only do that because if we need to do a go around, we need to make sure the propeller control is full forward. So bulk landing or go around or rejected landing, you see here, and I think the Duchess. One of the things I'll do, and one of the things your flight instructor should make you do, is you're in a complex aircraft, you have a constant speed prop. When we say go around, the first thing you should do is not push the throttle forward. The first thing you should do is make sure the props and then the mixtures, the mixtures and then the props and then the throttles go forward. Which is kind of hard to do because you've been conditioned to push the throttle forward, you hear go around. But now that you're flying a twin, or you're flying a constant speed prop, the first thing you need to do when you hear the words go around or make sure the mixture and the props are full forward first before you push the throttle forward. I really like in the Duchess here how it actually says step 1 is props forward, step 2 is throttles forward. And so in summary here, basically, when you're taking off, you need the blue lever full forward, and you oftentimes want to reduce the RPM during a climb, and it depends on the POH. Okay, so the 182 says you stay at the 2,400 feet for takeoff and for climb. The Duchess, I think, has you taken off at 26, reducing to 25 in the climb. The DA40 has you taking off with full forward, and then during the climb with full throttle, you reduce the RPM without reducing the throttle first. Just examples of looking into the POH for that specific aircraft and making sure you do what the manufacturers wanted you to do. When you're at cruise, then you set the powers you want, like we just looked at the table. Leave the RPM back during the descent. There's no reason to make more noise than necessary, and you could actually cause some harm to the engine by doing that. Before you land, however, you want that prop full forward or max RPM, and don't do it on downwind. The thing is, when you push the prop lever forward and the RPM jumps up to redline RPM, you're just making a ton of noise and just to anger your neighbors. So after you've slowed down is a good time for you to push that RPM knob forward. And so if next time you're hanging out at the airport and you hear somebody on downwind just go, that was them getting a little ahead of pushing the RPM control forward. So it's quieter for your neighbors, it's nicer for your motor. So again, generally, basically, I will do it on base. Sure, I go through my dumps check. I go in gas is on the fullest tank, undercarriages, down and locked and verified. Mixture is full rich. Propeller control, we're going to wait until base. And then I do a few other things, flaps and fuel pump switches and seatbelts all set. And then I go to base leg and I do it over again. I'll do, okay, gas is still in the full tank, undercarriage is still down, locked, and verified, mixture is forward, prop is full forward now, and flaps are coming down my next notch, fuel pump on for low wing, off for high wing, switches are set, that's my double check of my landing lights and everything else, and then seatbelt set, and I check and make sure my passengers are belted in. I roll out on final, and I pretty much do it all over again. Gas is still in the fullest tank, undercarriage is still down, locked, and verified, and that's when I usually have somebody else look at how many green lights there are and make sure. Mixtures forward, props forward, fuel pump, flaps, switches, and seatbelts. And I will check this each time on downwind, base, and final. So when you're talking to your flight instructor and they say, you should do it on downwind so you don't forget. Well, if you land without having the prop forward, you've missed it 3 times, at least twice, if not 3 times. So in summary, basically, we talked about air control, fuel control, and heat control in the last video. And this video talked about how you control the pitch and the RPM in that propeller. And a little bit about what not to do. So I want to thank you for listening. I'll get back off my soapbox now about RPM control and mixture control. And check back on Canvas for any other assignments that might be missed. And for what we're talking about next week, I hope you enjoyed this video, and thanks for watching. See you next time.